All right, let's go ahead and get started. In our next two sessions, we're going to be doing a survey of galaxies. We're going to start with galaxies that are outside of our own galaxy, and then we'll talk about our galaxy in detail. The reason we're starting with galaxies outside of our own galaxy is because they're much easier to see than our own galaxy because we aren't embedded in them. And so we can look out and see a whole zoo of different galaxies and different galaxy types and different structures of galaxies. So we can get a really full idea of what galaxies look like before we start studying one in detail. In addition to talking about galaxies today, you have a activity due on Thursday, which is mapping out our own Milky Way. Now, you're going to be doing this activity before we talk about the detailed structure of the Milky Way, and we're doing that on purpose so that you can learn about the distribution of material for yourself by doing the experiment that we've done to determine the size and extent of our Milky Way galaxy. So if you check out that activity, you'll find a little video introduction for that activity for Thursday. In the meantime, let's go ahead and get started talking about galaxies. Galaxies are collections of stars. They represent a sort of the structure which holds together all of the stars and planets that exist. And as we learned last time, the thing that really drives the structure of galaxies is dark matter. Dark matter is the thing that gives them their shape, it gives them their size, it gives them their star formation properties and all sorts of things like that. But of course, what really matters to us is the distribution of stars and planets because that's where we live and potentially creatures like us might live. So we're going to go through a whole collection of different galaxies and see some of the most recent images of what these galaxies look like. Now, a couple of things to keep in mind. Galaxies are really far away, so in order to study them in detail, we really need to determine their distances. And that's going to be the second part of this discussion, is figuring out how we determine distances to galaxies. Which is a kind of a challenge. Okay, so let's start with some of our deepest images of the universe. We've talked about the Hubble Deep Field before in our discussion of Olber's paradox, and I wanted to tell a little story about how we came to make the Hubble Deep Field, because I think it tells you some of the scientific discoveries that are still going on today when people are willing to take a leap of faith and just look to see what's out there. Back when Hubble Deep Field was first contemplated, this was after the launch of the Hubble Space Telescope and after its first repair mission. This was the first time we could really use our first space telescope to see deep into the early universe. And so what the director did is decided to look at the blankest spot of the sky, the darkest piece of sky that we'd never peered into before. And this piece of the sky, you can see it down here, was right near the Big Dipper. So if you go outside at night and look at the Big Dipper there, and there's the Big Dipper like that, this little dark patch of sky up here, which is about the size of the eye on the dime, if you hold it out at arm's length, very, very small piece of sky. And we zoom in on that to this little teeny tiny piece of sky right here. This is the image that we see, and this is called the Hubble Deep Field. This required 90 hours of observing with the Space Telescope, and it was effectively, we had no idea what we were going to find because every time we'd ever looked there, with every telescope before that, it was just blank sky. So this is what we see. The Hubble Deep Field is effectively a sea of galaxies. And if you look again, all stars have to have this diffraction spike to be a star because they are point sources, they're not extended sources. So that's a star, and that's a star. Every other object you see in here is a galaxy that contains tens of billions of stars. Hundreds of billions of stars. It's really a remarkable achievement to be able to look at this many galaxies all at once, and this is just this little teeny tiny patch of sky. So the question is, what is the distribution of these galaxy types? So they clearly have lots of different colors. What does that say about their formation history? And I should point out that this type of study of galaxies is an ongoing exploration in astronomy because galaxies, there are so many of them, they're so numerous, we've just begun to really classify them and see all the different types and shapes. of course, we're getting to the point now in cosmology where we're looking so far back that we can't even sometimes see the shape of the galaxy. We just see some of the fuzzy light from it because our telescopes aren't powerful enough to really resolve them. And so connecting what the colors are to these different shapes and sizes is really an open area of research in galaxies and cosmology. But since galaxies make up the bulk structure of the universe, it's something we need to study. Okay, so we'll start with Edwin Hubble, who was one of the first scientists to really study galaxies with big telescopes, and talk about some of the classification systems that were put in place early on for studying of galaxies. Now, with any classification system, it's going to be difficult to put objects into particular classes. Some are going to be really obviously one class or another. Others are going to be a lot more subjective in terms of where we place them. But we'll talk about the three major types of galaxies, and then we'll talk about some of the modern ideas about connecting all these things together. So if we look at the Hubble Ultra Deep Field, which is the Hubble Deep Field but taken with a much longer exposure, we can see better detail in the shapes and sizes of these galaxies. So we can look at these things and say pick one like this, which is a spiral galaxy. And spiral galaxies are very much their namesake. They look like little pinwheels. They have arms that stretch out like this. They have structure. Clearly star formation is taking place. Star clusters and bright stars occurring along these spiral arms. So they have a spiral shape, and they have this sort of flat, disky appearance to them. So these are the spiral galaxies. Now, contrast that with something called an elliptical galaxy. And again, named for the way they look, they're elliptical. They tend to be rounder. They tend to have older stars in them. You'll notice that in this galaxy we see blue and red stars. Right here, there's some blue and red stars together, making kind of an orange. In this galaxy, pretty much just red stars. So as you know, red stars are cooler. Cooler stars live longer. If we don't see any blue stars, that means we are seeing something that's older, and that means that most elliptical galaxies on average are older and more evolved than spiral galaxies. And then finally we have these things called irregular galaxies, and this is the catch-all for galaxies that are just bizarre looking. They don't really have any structure per se. They are all mangled for whatever reason. And these are just the leftovers from things that don't look like spirals or ellipticals. Now, what is the connection between these different types of galaxies? Well, that's what we're going to be talking about today. But I should also point out that there are other types of galaxies. Some are called dwarf galaxies. Most of those tend to be irregular. Those are smaller galaxies. There's also a connection between the galaxy colors and their shapes, and in a lot of galaxies you can only see their colors because they're so far away. But again, if you had an irregular galaxy or a spiral galaxy, they might have similar colors, and you wouldn't know if you weren't able to look at their shapes. So this is a tricky thing to be doing because we have to be able to have a telescope powerful enough to see the shapes of the galaxies and the colors to really see what's going on here. Now, some terminology for spiral galaxies. They tend to be disky, right? They're kind of a flat pancake shape, right? And this is, this looks round, but you can think of it like a plate that's seen not quite edge on. So that's called the disk. Then we have the bulge of the galaxy in the center. That's where the most, at least regular matter, is distributed. And then we have the halo, which is where the dark matter is distributed around the galaxy. Some galaxies have multiple types of components, right? We have the disk components. This is the Sombrero galaxy, and this is a very, very pronounced disk on this galaxy. It almost looks 3D because you can see the dust and gas. But this is an actual image of the galaxy. It's not a computer-generated image, which always blows me away. And then there's this sort of spheroidal component, what we call the bulge or the halo, that is in the bulge is in the center of the galaxy and the halo is on the outside. And so we can see that there's different components to this, which again makes this classification scheme of ours a little bit challenging because you can have disky ellipticals and you can have bulgy spirals, depending on the spectrum that we're looking on. Here's just another picture to show the distribution of ages for these different components. You'll notice when you look at this that the center of this galaxy is red, right? And the disk part out here is blue. So that tells you instantly that these stars have to be younger and these stars have to be older, right? Because we don't see the blue stars in the center, they've all evolved away. So we can tell that the old stars tend to be concentrated in the center, and the younger stars are all in the disk formation. That tells us that the active star formation is happening in the disk. Now, what about the distribution of their orbits? In the center of the galaxy, we tend to have orbits that resemble sort of globular cluster type orbits. These sort of, plunging, highly elliptical stellar orbits like this. And on the outside of the galaxy and the disk, we tend to have more of a circular orbit, but it tends to bob up and down along the plane of the galaxy. Right, so you can track the orbits of the stars. So it just gives you an idea of the different types of paths that stars take around the galaxies. Galaxies also have components. Some of them have these bar components in the center, and that's again due to the dark matter distribution of the galaxy. It will create a different gravitational potential that the stars move in, and these bar shapes can form, just representing the distribution of matter in the galaxy. I have to point out though that what you're seeing here are not. It's not as if there's a bunch of stars that just hang out in these spirals, right? These spirals have star formation occur in them, but stars move in and out of these bars and spiral arms all the time. So if you imagine the overall structure is put in place by the dark matter, causing star formation that kind of slowly moves around, and stars move in and out of this thing, and star forming regions move in and out of this this overall structure, creating what we see as the barred structure of the galaxy. Now let's look at kind of a combination of these things. If we have something that's has a disk, but less dust and gas than we expect from a spiral galaxy, this is something called a lenticular galaxy. It's a combination of a spiral and an elliptical. Now how did this happen? Maybe we had galaxies collide. Maybe we have a spiral or a elliptical galaxy that's finally getting rid of its gas because it's older. These are all possibilities for how we can get these sort of combinations of galaxies. The difference between galaxies and stars is that galaxies are relatively big compared to their distances between each other. So we can get a lot of interaction between galaxies that we don't really see with stars. And so we have to accept the fact that sometimes we'll see galaxies have merged together. Now here's an elliptical galaxy with virtually no disk component to it, so there's no active star forming. The stars are very old. They're all red. We don't see any very much dust or gas. It's all been used up making stars, and it has this spherical shape. This is kind of a classical spheroidal elliptical galaxy. All of the stars in this galaxy are going to have these kind of randomized orbits. So that's the reason why it looks circular, is you've got stars that are orbiting in all inclinations. Here's the Large Magellanic Cloud, one of the closest irregular galaxies to us. It's a companion galaxy of the Milky Way. And again, you can tell by looking at it a couple things. You can tell that it has to have young stars in it because I see blue stars. There's dust and gas, so we have star forming. But other than that, it doesn't really have any structure. And part of that could be because of its interaction with the Milky Way. It doesn't have the ability to form a lot of this structure. And it also could have interacted with other galaxies in the past that would give it this kind of irregular shape. When Edwin Hubble was studying these, he put together this classification scheme based on the galaxies he was seeing, and he classified galaxies as one of three types. If we exclude the irregulars, irregulars are kind of in their own class over here. If we just think about spirals and ellipticals, there were really three classes. There were two types of spirals: the regular spirals that have a circular bulge in the center, and you have loosely wound spirals, tightly wound spirals, and very tightly wound spirals, so that we've got the SA, SB, and SC. And then we've got our barred spirals, again, loosely bound with very distinct arms, more tightly bound, and more tightly bound still. So that gives us a distribution over the types of spiral arms that you can have in a galaxy. And then we have our elliptical galaxies, like this, and depending on how circular or elliptical they are on a continuum from E0 to E5. And then kind of in between here are these S0 and SB0, which are barred, mostly spheroidal type galaxies, but clearly have a disk component to them, right? Again, this is not to suggest any kind of evolution from one to the other. This is just displaying them on a spectrum so you can see the types of galaxies that we have. Okay, so once you've got galaxies, you look out and you see that galaxies tend to cluster up in groups, and those groups are called clusters of galaxies or groups of galaxies. They can be pretty extensive, right? This is a picture of hundreds of thousands of galaxies. You can see these Einstein rings from gravitational lensing from background galaxies. You can see, every single one of these things is a galaxy. This is a very rich cluster of galaxies. And these are elliptical galaxies, and these tend to be common in huge clusters. So these huge clusters tend to aggregate these elliptical galaxies. So maybe that tells us something about the formation processes that form these elliptical galaxies when we see these enormous clusters of galaxies. You can see some barred spirals here. Here's a barred spiral here. You can see some disky looking galaxies here. You see some ellipticals. And again, there's just so many out there in these large clusters, sometimes hundreds of thousands of galaxies. Whenever I look at a picture like this, I have to kind of stop and pause and say, think about what you're looking at. You're looking at hundreds of thousands of galaxies containing hundreds of billions of stars each. Okay, so we've talked a little bit about the shapes of galaxies. More importantly is that galaxies map the structure of the universe, which is what we really want to talk about. And so we need to figure out a way to measure the distances to galaxies so we can map the overall structure of the universe. We can see all the way back to the cosmic microwave background. It would be great if we could figure out the distances to galaxies all the way back to the cosmic microwave background. And it turns out that's possible now after about 100 years of work on this problem. So just to recap, when we find distances, we have to kind of bootstrap ourselves up. And the first thing we have to do is determine the size of the solar system. Now, we talked about the distance ladder as it relates to finding the size of the Earth and finding the size of the Moon and such and so forth. But in the modern era, we can figure out the size of the solar system by just using radar. We bounce radar signals off the planets. So that's step one, determine the size of the solar system. Step two, we've done this as well, learn parallax. Using parallax, we can learn the distances to the nearby stars. We just take measurements in January and July, and we get the distance to the nearby stars. Once we've done that, we can create the HR diagram, which allows us to figure out the distances to stellar clusters. If you know its actual brightness, then you can measure its apparent brightness and figure out its distance, right? So if we know the distance and we know the apparent brightness, we can figure out its actual brightness, and this gives us the ability to tell the properties of the stars by creating HR diagrams and things like that. Once we have HR diagrams, we can start to do measurements of stellar clusters, and we've done this as well. Stellar clusters tell us the distance by looking at the shift of the main sequence up or down relative to some standards. So in this case, we've got the Pleiades and Hyades, and you've seen these data before. There's the main sequence of the Pleiades, main sequence of the Hyades. The relative apparent brightness is 7 times greater for the Hyades. So we can say, well, if its brightness is 7.5 times greater, it must be the square root of that closer. And we can determine the distance to these things relative to a standard such as our sun. So we've done this one as well. So if we can find a cluster, we can tell the distance to whatever object we're talking about. If we get the cluster's distance, we can determine the luminosity of every star within it and each star type. And that allows us to do an analysis of all of the stars in that cluster to see if there's some other properties we could tease out about the age and about the properties of the stars in a cluster, so that we could maybe use those properties to determine the distance. Because even the clusters of galaxies are relatively difficult, or clusters of stars in galaxies are relatively difficult to see if they're really, really far away. So it'd be nice if there was some bright object that we could use as a distance indicator. And it turns out that there is. If you recall from your stellar evolution, we have stars that evolve off the main sequence after they stop burning hydrogen into helium, move up to the main giant branch, and they begin to fuse different elements, and they have shell burning where they fuse successively higher elements. That shell burning causes the star to basically pulsate, and that pulsation period allows it that pulsation period depends on how bright the star is. So if you have a particularly bright star, its pulsation period is going to be different than a particularly dim star for these types of stars called Cepheid variables that are in the instability strip. Now, that means that this pulsating star, you don't have to be able to observe the cluster. You can just observe the one star. And as long as you can measure the pulsating period and you can measure its apparent brightness, the pulsating period will tell you its actual brightness, and you can measure the distance to it. And this is the relationship we get for Cepheid variables. So you imagine finding Cepheid variables in all of these clusters of galaxies, or clusters of stars. We find all these Cepheid variables, and we can measure their period easily enough, and we can know their luminosity because we already know the distance to the cluster that they're in. Which means if I find some isolated Cepheid variable with a period of 100 days, I can just go on this chart and figure out what its luminosity is. Again, if I know its actual brightness, I can measure its apparent brightness, I can get the distance. Luckily, Cepheid variables tend to be pretty bright stars. Another bright distance indicator is something called a white dwarf supernova, or a type 1a supernova. These supernova are interesting because they are formed when you have a white dwarf and you have some other star that's near the white dwarf. That material from this star gets stripped off due to the white dwarf's gravity and spirals onto the white dwarf. If the white dwarf achieves a certain mass, it's going to turn into a neutron star and explode. And it happens at the exact same mass for these types of objects, and and that same explosion at that mass gives you a brightness which has the same peak brightness regardless of the object that we're talking about. So the peak brightness is what we look at. That tells us its absolute luminosity because we find these things happening in things we know the distance to. They are also exciting because they outshine the entire galaxy. This is a white dwarf supernova. This is a galaxy that white dwarf supernova was found in. It rivals the brightness of the galaxy for a short period of time, so we can determine the distance using the white dwarf supernova as a standard candle. The advantage to these supernova is that you can see them at great distances. And that means anytime you can see a galaxy, since the supernova rivals the galaxy, you can see the supernova when it occurs. And the really cool thing about this technique is that it's really easy to do. You find a galaxy, you wait, keep observing the same galaxy, hopefully someday you'll see a supernova and it just pops up. Right? Now, the advantage to this is that if you look at hundreds and hundreds of galaxies, on average, a supernova occurs in a galaxy once per year. So if you looked at hundreds and hundreds of galaxies, then on any given night, you should find a supernova. And this is what people do to determine the distances to these distant galaxies. We can go out to 10 billion light years with this study and even further using these things as standard candles. So again, we had to have all of this stuff together because we have to have overlapping measurements in order to check the distances. So if we look at radar gets us out to the outer solar system. We can check the outer solar system with parallax, make sure that works. Parallax gets us out to the nearby stars. Nearby stars include some clusters, which means we can get the main sequence fitting to double check here and sort of tie these things together. The main sequence fitting, which is the HR diagram, takes us out to the point where we can look at clusters that have Cepheid variables in them. Cepheid variables are things you can see in nearby galaxies, so we can get out to some of the kind of nearby galaxies. Nearby galaxies are ones that have supernova in them, we know the distances from Cepheid variables, and then once we've got that, the distance standards get us out to distant galaxies. So effectively, we are measuring these distances through this thing called the distance ladder, and it kind of looks like a little ladder there, stepping up one to the other. So this is a challenge, but it's something we've just managed to figure out how to do in the last 100 years. The last step in this is the Hubble law. The Hubble law gives us the distance pretty much anywhere we want, because once we know about the Hubble expansion, you can measure distance by measuring the velocity of the galaxy, which is pretty easy. So this is giving us something that allows us to map the structure of the universe. Okay, there's one other thing I want to show you. So this is the Sloan Digital Sky Survey was a survey of much of the night sky that was designed to effectively map the distances to these different galaxies. And the way that it works is they would use spectroscopy to measure the velocity, that the recession velocities that these galaxies had, and then use that and the Hubble law to get a distribution of distances. So let's go ahead and take a look at this. So we're going to go ahead and zoom out here and look at all of these different galaxies that have been measured with the Sloan Digital Sky Survey, and you'll start to see the structure of the universe unfold. So the Earth is right at the center of this, our galaxy is right at the center of this, so we are looking from our vantage point, and you can start to see that there's structure to the universe. There are gaps and voids and walls and all sorts of shapes that emerge where we can see the distribution of galaxies and clusters of galaxies and where they've formed. Now the shape of this, the reason it's in slices is because the Sloan Digital Sky Survey didn't survey the entire sky, it just observed a lot of it. Now if we go out even further, eventually you get to the cosmic microwave background, and we've simulated that by putting the cosmic microwave background around this. And now what you're seeing here is effectively the observable universe. So we can see the distribution of the cosmic microwave background, we can see the distribution of galaxies and galaxy clusters, and we're right at the center of the observable universe. And the only reason we can't see any further out than this is because light hasn't had a time to reach us yet. So this is the universe as it was, this outer shell, 13.7 billion years ago. And there hasn't yet have time for us to see anything beyond this. So this is unknown. Although, given the size of the universe that we see, we suspect it looks an awful lot like this. So let's just play this again. So again, we measured the distances to all of these galaxies using Hubble's law, so we can put their three-dimensional shapes in because we know the direction we looked at. And one thing I want you to notice as we're zooming out again is that these walls and bubbles and everything kind of matches the bubbliness shape of the cosmic microwave background, and so there's clearly a connection between the origin of the universe and the distribution of material that we see right now. That's just beautiful. And these little blue dots are something called quasars, which are very high energy active galactic cores that we can see from a great distance away. And that is our universe. So again, galaxies tell us the distribution of material in the universe. If we know the distances to the galaxies, we can determine the size and shape of the universe. And with that, we will move on next time to talking about our galaxy in particular.